Hi, and welcome to Developing Mathematical Thinking with me, Rory Dearlove. I am a lead practitioner at John Donne Primary School, and I also, as well as doing some LSE work for London South Teaching Schools Alliance, I'm also NCETM Mastery Specialist, which means I work for the Maths Hub supporting schools with their maths offers in the local area. So what do we mean by developing mathematical thinking? Well, one of the things we talk about is number sense. So just to get us warmed up, have a look at this question and have a go at answering it. You can pause the video if you want. Now, I'm sure some of you have used the formal written method and followed the algorithm carefully. And other of you may have thought about what you know and use that to answer the question flexibly and creatively. Now, both of those methods will get you to the correct answer. But there are certain advantages in developing number sense so that children can think flexibly and creatively when solving problems like this, and not relying solely on written algorithms. They can be quicker and more efficient, and often they're more elegant. I'm sure that lots of you will have seen questions such as these in SATs and other tests, and seen children work towards the formal written method and take up valuable time that could be used solving other questions. So, what are the other things that we want for children in maths? We want them all to achieve to a high level. We want that learning to be deep and sustainable and stay with them throughout their educational careers and beyond. We want them to have the ability to apply that learning in different contexts, both in the classroom and outside of it. We want them to be able to reason about the concepts and make connections between what they have learned and what they are learning. And just as importantly, we want them to have a belief in themselves and an enjoyment of maths. Now, one of the ways in our school that we have looked to foster that belief and enjoyment of maths is by building a mathematical mindset community. Now, if you want to know more about this, there is a link on the last page to the UCubed website, which is run by Joe Bowler in conjunction with the Stanford University. So, some of the principles of developing a mathematical mindset community, as well as believing that children can achieve to a high levels, we also make sure that we value communication and connections. So there's a lot more talk in our lessons than there might have been previously. We make sure that the maths is visual, not just lower down the school, but throughout. And we make sure that the maths is open so that children can investigate and explore problems in different ways. And this helps them to see the wonder and the curiosity and the beauty of maths, rather than seeing it as a load of ideas that need to be remembered. And the other thing that we do is we create a risk-taking and mistake-valuing environment. One of the things that I have found really successful is talking about really good mistakes, so that children know when they highlight a common misconception, they are contributing to the learning just as much as somebody who gives the right answer. Now, why is this all important? It's because we are teaching children to be learners for life, and we're setting them up for going into the real world. And the real world is, changing, is changing by the day. At least that's quite old, but I think they reflect, give us an idea about what employers and what the world is looking for in young people. So it's not about sort of written skills and writing skills, although those are all obviously important. But the things that are really valued are teamwork and problem solving, interpersonal skills, oral communication, and listening skills. And we are doing our children a service if we do not give them opportunities to develop those in our lessons. So one example of a rich mathematical task is one below. Now pause the video and have a look and consider how you see the shapes growing. You may find it easier or beneficial to draw. Now, there is not one right answer to this question. There are many different ways that the shapes can be seen to be growing. I'm going to share a few of you now, but this is not an exhaustive list by any means. Some of the more common, what was really beneficial is to give them names. You can give them names like we've done below, or it is also sometimes valuable to give them the name of a child. So we can talk about Anthony's method or Jawan's method. And that's one of the things that we can do to help children see themselves as mathematicians. So have a little look at the different methods and see if yours is there, or maybe you thought something different. Now, why is this important? Because it's the teacher's job to organize and provide experiences which enable pupils to construct and develop their own understanding of mathematics, rather than simply communicating the ways in which we themselves understand the subject. And by having these open-ended lessons where there is not one correct solution, it encourages talk and it encourages children to explore and do the thinking for themselves. So in when I've done this lesson, we'll have some of the children who are sometimes less confident get on with it better than some of the children who are often more confident, because they are not just looking for the answer and they're not just satisfied by having one answer, but they explore it and they look at the different ways. And actually, it really fosters the talk amongst the children and develops all those skills that we talked about before. Now, that is not to say that there are some solutions that are perhaps more elegant or more useful than others. So for this problem, a really useful solution is the square method. But if I just show this to the children straight off the bat, then they're not really going to be able to engage with it to the same level as if I've given them time to explore their own methods. So by giving them this method, I can say that this is one of many valuable ways of doing it, but this one has some added benefits because it's really useful in helping us predict or know how many squares or there will be in the 100th shape or the 10th shape. Because what we can see here is that each shape, the number of squares, is equal to the square of the shape plus 1. So n squared plus 1. And even children who have no experience of algebra are able to see that. They will know that the third shape has the same number of squares as 4 times 4. And the fifth shape will be 6 times 6, and the 10th shape will be 11 times 11. And because they've had the experience of looking at their own ways that the shape has grown, and then they can understand this method, they're able to understand that much better than children who just work with numbers and without working visually. So that brings me on to the 5 big ideas of teaching for mastery. Some of you may be familiar with this. Now, today I'm really going to focus on the representations and structures as a tool that you can use to develop children to think mathematically. Helps children to access to learning, helps them to recognize patterns, and helps them to make connections between different areas of maths. And really see maths as a few big ideas applied in different ways rather than a load of different rules that need to be remembered. Now, when we're working with representations and structures, it's important to think about the different learning modes. And some of you will have been familiar with these and Bruno's research on the subject. So Bruno talks about the enactive, the iconic, and the symbolic. But often when we're talking about this in maths mastery, we talk about concrete, pictorial, and abstract. And I'm going to give you a little visual representation of what I mean when I'm talking about that. So in the context of times tables, one of the things that we have been doing in our school is always starting with the concrete. So we think about what comes in twos, what comes in fours, and then quickly moving to thinking about how that can look in an array. Because an array is a really useful visual representation of a multiplication sum or multiplication calculation. Sorry. Now, it's only once we've had experience with the concrete that we start moving on to the visual. And you can see the small step in drawing the arrays rather than making the arrays. And it means that we can play some games that help to explore this. How Close to 100 is a really popular activity on the Euclid website, and it's something that I've done successfully with children all the way from year 2 all the way up to year 6. And we can adapt it by using different dice and different size grids. How the game works is you roll 2 dice, or if you want 1 dice and times that by a fixed number, and then you draw an array that represents that calculation onto the square. And it really helps children to make a connection between those equations and their visual representations. Now, it's only after they've had this concrete and this pictorial experience that children are able to go on to working in the abstract. And what this means is when we are working in the abstract, we can work well beyond just reciting times tables or being able to answer a simple times table test where I say 7 times 3 and you write down the answer. But children can really think about it in these flexible and creative ways. Now, at this point, I'd like you to pause the video and have a little think about the ways that you might have used concrete and pictorial representations in your classrooms. So, I'm sure lots of you will have thought about place value, and there are many other ways that it could be applied too. I just wanted to have a look at one way that we looked at that concrete resources can be used to represent place value in a way that we might not have thought of before. So often when I work in other schools, they say that they're really good at using concrete materials and down in early years and in year one and possibly even in year two. But by the time they get up to year six, they've often gone away. Shouldn't be the case. Have a look at this. And if I tell you that this thousands cube represents 1, can you think about what this 100 square and this 10 stick and this single unit represent? Now, once we've discussed this as a class and we recognize that the square represents 1/10 and the stick represents 100th and the single square represents 1,000th, then it can really help us to understand place value when we're working on numbers that have decimals or numbers that are less than 1. So thinking back on what we did, give you a little preview there. Think about which number is bigger, 0.21 or 0.203, and the misconception that children might have with this. So a misconception can often be that 0.203 is bigger because it has 3 digits. And I've always learned that the more numbers, the bigger the number. 203 is bigger than 21, so obviously 0.203 is going to be bigger than 0.21. And it can be really difficult to explain this without using, appropriate visual representations. But when I represent it using the concrete materials, it becomes much clearer. You can see that 0.21 represents 2/10 and 100th, whereas 0.203 represents 2/10 and 3,000. And it's really clear by using this visual or by making these numbers, with concrete resources, which number is bigger. But it's really important to understand that visual representation is not equal understanding. It's not enough on its own. And if I had done that previous example just by showing the children, some of them might not have got it. And actually, if I was to teach that lesson, and when I have taught that lesson, I make sure children have lots of time to make their own numbers, using the concrete resources to make different numbers and compare them and explore them. A really good example of how visual representation does not always lead to understanding is represented here. So when I add 4/5 and 2/5, I could visually represent it like this. Now the result is 6/5, and we can see that there's one whole and one extra fifth. But for some students, they would say that the result would be 6/10, because the pizza has 10 parts and they take 6 among them. And we could have a think about what is wrong with that response and what we could do to correct it. So what we need is to give children experience to explore that and give meaning to those tools. They're not just supports for learning. It doesn't happen automatically. Children need to construct the meaning. It's not just watching demonstrations. It requires working with those tools over extended periods of time, trying them out and seeing what happens. It doesn't reside in the tools. It's constructed by the children as they use the tools. So it's really important that children get lots of hands-on experience with these materials. And one thing that I would definitely say is when you introduce a new tool, it's important that children just get some free time to explore it. The amount of time that is will vary depending on their age group, but it's a valuable bit. We all do it. When I put some materials in front of you now, you'd pick them up and you'd have a look at them. Yeah, that's an important part of the learning. We need to do that before we can start giving them meaning and using them to solve problems. So getting these concrete materials in as early as possible is really important. And then we can slowly move through the process, getting more abstract as we go along. A tens frame is a really useful structure for exploring addition and subtraction. And it's really one of the things that we've had real success with down in our early years is these buses where the children make themselves and they can make stories about putting their friends on the bus and off the bus. And work with adults, we can support them to start thinking in more mathematical ways. And one of the ways we can do this is to use their subitizing, which is where we can recognize a number without counting the objects in it. And 10 trains are really supportive of this because of their structure of 5 and 5 and 2, 2, 2, 2, 2. And children can, maybe move from counting at 2, 4, 6, and to this method where they would see that there are 5 and one more people left. So 5 and one more person left, 6. Now, these experiences of working with the materials means that we can start to use them in more sophisticated ways and use them to support children explain their thinking as they move through the school. So, challenge for you now. I've got a problem for you here, 24 plus 9, and I've deliberately put the answer because I'm not so interested in the answer. I'm really focusing on the methods that you use to solve this problem. Now, if you have access to the concrete materials, fantastic. If not, you might need to work visually. So you might need to draw your 10 frames, and maybe using 2 colors or squares and circles, can you represent how you would solve this problem? 24 plus 9. And I've deliberately laid the 10 frames out and I've scattered them across the page because I don't want to lead you in one way or the other. So take plenty of time, and if you think you found one way, perhaps explore another way that you could solve it. Pause the video here. Now, let's see if some of these solutions represent your methods. Because there is not one way to solve this, and we could use a formal written method like we looked at before. But actually, we don't want children to be slaves to the algorithms. We want them to be able to think creatively and flexibly, using mental strategies where they're efficient. And you can see here that there are different ways to solve this problem by either partitioning the first or the second addend, and then applying what we know about our number bonds, not just 210 and 220, but within 10 and within 20, which are so important for children's mathematical thinking to solve this problem in efficient ways. Now, if I were to teach that lesson, I would have already anticipated the response that children would do. Now, if you would like to see what that looks like, I put a link at the end to a lesson that I taught with a colleague in Shanghai based on their phase 3 mastery principles, which use children's responses to drive the learning. So it's thinking about what would be an efficient and elegant way that children could solve the problem, and what might be some of the misconceptions that they might make in doing that. And what I would do is, while children are wrestling with the problem, so I would go around, and instead of supporting them to get to the right answer, because the answer is less important than the process, I'll be looking for children who are using efficient and the strategies that maybe we want to promote, and children who are making misconceptions or making mistakes that might be useful to highlight to the rest of the class. And then using a visualizer or concrete materials on the board, I'll get the children to represent their thinking so that as a class, we can recognize those misconceptions and that we can see the value of those more elegant solutions. So this lesson was about subtracting through 10, and you can see how we apply that principle in different phases of the lesson, working first with concrete materials and then working pictorially before finally moving on to the abstract. This is quite a structured method here, but we can actually, with enough planning and enough preparation, allow children a bit more freedom on those problems. And in Japan, they call this teaching through problem solving. And in this structure, we allow children to grasp the problem, and we give the problem quite cold. We don't sort of suggest this a method. We just give them the problem. And this problem needs to be just beyond what the children have been learning, so they can apply what they know, but they might actually come across some new learning. They might have to try and learn something new as they do this. And then we give them quite a long time to try and solve it. And again, it's not the teacher's job to go around and make sure they get the right answer. They might have some prompt questions or guide their thinking a little bit in one way or the other, but they're not trying to get to the right answer. It's fine if we get to the end of this section and they've not got to the right answer, because the next stage is where we present and we discuss. And the teacher will have through moving through the class, seeing children using different methods of varying degrees of efficiency. And then they will choose, and they will have anticipated already, how to present those different methods in a structured way to guide the children's thinking towards those more efficient, those more elegant solutions. And at the end of the lesson, that learning will be summarized and reflected upon, and the new learning is brought out of that. So to give you a little bit of an example of that, one problem we saw was this one. And it's where children had already been taught how to divide, and they'd also been taught that sometimes when you divide, there is a remainder. Now they were given this problem. 24 children and adults go on a school trip, and as part of the trip, they will go on boats. And each boat can take 4 people. How many boats will they need? So have a think now quickly, and think about the different solutions that children would have come to, and what might have been some of the misconceptions they would have made. Pause the video if you'd like more time. Now, as I'm sure you'll anticipated, lots of children said that they would need 5 boats, remainder 3. And some children came up and they showed that in different ways. And the teacher didn't say, no, you're wrong, but they said, does anybody disagree with that? Does anybody think something different? And she'd anticipated this girl, and she'd asked this girl to come up and show her solution. And using the concrete materials on the board, she was able to show that actually you needed 6 boats. Because if you didn't have 6 boats, there'd be 3 children who wouldn't get to go out on the water. And through the children's experience of tackling this problem, they could see that that was the correct answer. And through discussion, they came to the conclusion that whilst if they just use the algorithm, they get a remainder, that actually for this problem, a remainder didn't make sense. And that was the new learning, that for some division problems, a remainder is not appropriate response. So this was another way that you can develop mathematical thinking. So hopefully that's been a little bit of a whistle-stop tour around some of the different tools that you have to develop mathematical thinking of children in your solution, about how using materials and the different structures in your lesson can help children to develop that number sense and be able to think, creatively and flexibly rather than just using written algorithms. And how this can set them up to be lifelong learners who can apply what they have learned both within the classroom, but also wider, and become sort of more confident team players, creative, flexible thinkers. So thank you very much for listening. And if you'd like to know more, I put some links here for you to use. All right. Thank you very much. And I will stop the session now.